Welcome everyone. For today's prep, we're going to be looking at the substitution rule for indefinite integrals. And well, let's start with the rule. And we have it written here as a formula. We're not really going to think of it as a formula to memorize. We're going to think of it more as a process. And before we get into this, this is really related to the chain rule that we saw for how to do derivatives. So a lot of the integration techniques that we see are, well, they're kind of undoing the derivative rules. So this one is related to chain rule. And chain rule was a way to differentiate the composition of two functions. So if you remember the chain rule, what did it say? It said if you had an outer function and an inner function, the way you calculated the derivative is you would differentiate the outer function and then keep the inner function the same, and then you'd multiply by the derivative of the inner function. So with substitution rule, we're trying to reverse that. And we're going to use a lot of the same terminology though. So in particular, we're going to be trying to integrate this complicated function here. So f of g of x times g prime of x. And we're going to have this complicated integral. And the idea is we want to see if we can identify what the inner function is. And we're going to simplify it. We're going to call it, just give it a name u. So just like with chain rule, we use that inner function, outer function terminology. We're going to do the same thing here. So we're going to let our inner function, we're going to call it u. And the idea is, once we make that identification, then we'll be able to kind of swallow up this g of x and replace it with just a single variable, u. Now there's a little bit more going on, because then we have to deal with this inner derivative that we get from doing the chain rule. And we're going to calculate something called, well, we've used this term before, but let's review it. The differential. So if we're letting u equal g of x, we're going to calculate the differential du by differentiating the function and then multiplying by dx at the end. And the idea is we're going to use this differential and we're going to replace the g prime times dx with du. So after all the dust settles, what we're really doing is we're identifying that that inner function, and we're just trying to cram it back into the function, and to simplify, just to kind of identify what that outer function is. And then that's what we're going to be really finding the antiderivative of. Okay, so right now it's a little abstract. Let's try an example to see how this works. So example 1, we're going to integrate the function 3x plus 4 raised to the power 10 times 3. So this entire thing here is the function we're integrating. So we're finding the antiderivative with respect to x. All right, so we're just going to go through, see how the process of substitution rule works. So the first step is we want to identify u and then calculate du. Well, I shouldn't say identify. Let's choose, because sometimes what makes this tricky, sometimes there's more than one right way to do these. So we're going to choose u and then calculate du. All right. So how do we choose u? Well, we'll get into the strategies, but for right now, I'm going to tell you what u is. But generally, if you see parentheses, the stuff inside the parentheses, we're looking for the inner function, usually that's going to be your choice for u. So we're going to let u equal 3x plus 4. Okay. Now, once you've chosen u, your hand is forced. So forget about everything else for a second. And we're going to calculate the differential. So differentiate your function. So derivative of 3x plus 4 is just 3. And then we multiply that by dx. Okay. So then we can go back. So once we've chosen u and calculated du, the next step is to actually substitute these things into our integral. So we're going to substitute in our choice for u and d and what we calculated for du. All right, so this is where we it's kind of like a puzzle, and we have to see how the pieces fit back in. So our choice for u, by design, we're going to be able to fill that in right there. And if we look at the remaining terms, we've got a 3 times dx here at the end. And what do we got in our differential? Well, it just so happens, very nicely, perfect fit, we've got a 3 times dx. So we're going to replace that 3 times dx at the end there with our new differential du. So we're substituting those pieces in. And if we make the substitution, we're kind of swallowing up that whole 3x plus 4, and we're just consolidating it into a single variable u. So it's going to be u raised to the power 10 instead of that 3x plus 4 raised to the power 10. And then this 3 dx at the end becomes our new differential. So we've got a du there at the end now. And the upshot of all this is we've taken a complicated integral, and now we've gotten it down to an integral that's just one of our basic antiderivatives. So this is now just basic power rule. And once we've gotten it to that point, we're ready for the next step. So the next step is to just do the integration. So we're going to get our antiderivative. All right, so we're integrating u raised to the power 10, finding the antiderivative, now with respect to this new variable u. So if we do our power rule, our variable is u. We're going to add 1 to the exponent, so that's going to take us up to 11. And then we take that new exponent, flip it, put it in front, so we get a 1 over 11 in front. And whenever we're finding a general antiderivative like this, we want to remember our plus c at the end. All right, so we're done, almost. The last thing we need to do is we have to go back to the original variable. So our function that we started with was in terms of x. Right now our antiderivative is in terms of u, so we got to go back. And we're going to plug back in. So that's our last step. So we're going to plug back in for x. All right, so we know what u is, and it's 3x plus 4. So we're just going to fill that in. So we had the 1 over 11, and then instead of u, we're going to write the 3x parentheses 3x plus 4, and then our raised to the 11 plus c. So we're kind of converting back there. And that's our antiderivative. All right, so let's try another example. Really, it just comes with practice. So in class, we'll go through some of the strategies on how to pick u, but generally, you're looking for parentheses. So if you see something parentheses raised to the power n, like we had in that last example, you're going to pick u. You're going to let u be the term inside the parentheses. If you see a fraction with just some stuff floating around in the denominator, you're going to let u equal the stuff in the denominator. And that'll give you this integral of 1 over u or something similar. And if you see an exponential function and you see a bunch of stuff up in the exponent, chances are you're going to let the u equal the stuff inside that exponent. So you're really looking for, again, we're trying to identify the inner function. But let's try another example. Let's try one with the exponential. And the way I had that table organized, you're looking for the complicated part of the function you're trying to integrate, which you want to kind of break your function up into pieces, and you want to look for the more complicated piece. And in that complicated piece, that's when you're looking for the parentheses and the inner function. So let's try example 2, and we're going to evaluate this integral. The function is 2x times e to the x squared dx. So when we look at this function, there's kind of two pieces. We've got the e to the x squared piece, and then we've got this 2x. And you want to look, which of these is the more complicated piece? Well, that exponential, a little bit more going on there. And so we see an exponential, and we want to think, what is the inner function for that complicated piece? Well, the inner function is the stuff that's up in the exponent. So our first step again is to choose u and calculate du. So our choice for u, we see that exponential term. We're going to let u equal, and there's not just x. It's not just a plain x up there. There's more stuff going on. So we're going to let u equal the stuff that's in that exponent. All right. Now, one thing that can be helpful. Well, let's actually get the differential first. So, again, forget about everything else. Just zoom in on once you've made that choice for u, your hand is forced. So we're going to calculate du. Differentiate the x squared. We get 2x. And then for our differential, then we multiply by dx. Okay. So step 1 complete. Now we want to substitute these pieces in. And one little strategy that can be helpful is just to rewrite your integral. So take that complicated piece and write it first. So I'm just going to rearrange these terms a little bit. I'm going to flip them around. So I'm going to move the complicated piece in front of this random 2x that we have floating around. So I'll put the e to the x squared first, and then times the 2x, and then the dx at the end. Excuse me. All right, so why do we do that? Well, those leftover terms normally in some way get incorporated into our differential. So it helps to have those loose terms next to the differential to see how the pieces fit together. All right. So let's see how everything's going to work. So we know that x squared is going to become u. So we're going to fill that in. And then we also see we've got the 2x dx at the end there. And we got lucky. Just so happens in the differential we calculated, we've got 2x dx. So that 2x dx is going to become our new differential. So it's a perfect fit. And we're going to see it's not always a perfect fit. Sometimes the leftover terms don't match up perfectly with what you're calculating. We're starting off easy. Everything, all the pieces fit together nicely. All right, so that was step 2. Substitute in. All right, so now that we do that, what do we end up with? Well, instead of that x squared, we're going to end up with e to the u. And then instead of that 2x dx, we just end up with our new differential du. And now this is one of our basic antiderivatives, so we can just do it. So that's our next step. We get the antiderivative. This is something we can just do. So what's the antiderivative of the exponential function? Well, it's nice. It's its own antiderivative. So it's just e to the u. Don't forget our plus c at the end. And then our very last step is to convert back to x. So we want to go back to x, or whatever the original variable is. Okay, so there's our antiderivative. And the nice thing about this is you can always check your answer. So, if you think you may have made a mistake somewhere, how can we check this? Well, the idea is we can take that answer that we got, and if we differentiate it, we should get back the function that we started with. So let's try it out. E to the x squared plus c. We're going to differentiate that thing. And if you use substitution rule to get the antiderivative, you're going to have to use chain rule to get the derivative. So let's differentiate this. We see a general exponential function, so we're going to have to use our general exponential rule. Differentiating c, that's just going to be 0, so we don't have to worry about that. And how does differentiating a general exponential function like this work? Well, the exponential part stays the same, and then we multiply by the derivative of the exponent. And derivative of x squared is just 2x. So we end up with e to the x squared times 2x. And, yep, that's precisely what we started with. So that tells us we did it good. All right, so you don't have to show the check as part of your work, but if you want to check your work for any of these antiderivatives, that's a good way to do it. Differentiate, you should get back what you started with. All right, so we're going to practice this more in class. So substitution rule is probably the most fundamental integration technique. We're going to see it in Calc 1, and then you're going to use it a whole bunch in Calc 2. So I think really just practicing as many examples of these is really helpful. So that's what we're going to be doing. So I'll see you then. Bye-bye.